Maybe. So now I've learned that at the beginning of the recording, it shows me coming over here because it's already recording, but it's asking me if I want to. Interesting. Hello, everybody. So that's that. All right, now, please look at your test. We can discuss problems that happened on the test. As I say, from my point of view, they were supposed to be pretty easy. I actually gave you a test that I've given people in class in 50 minutes and without any extra help, meaning books and notes and WebAssign, all that. But I thought, well, let's make people feel better. Hopefully you'll do better. I thought if everybody got 40 or low on this test, I'd probably just say, I'll drop. I'm joking again. But fortunately, a lot of people did better, so I hope you feel a little better now than you did earlier. Generally, a couple people dropped a few points, but most people did better. A lot better for some people. Okay, so we are in chapter 3 officially. You have a test out there that's due tomorrow night. I wouldn't start it tomorrow night because there's a couple of little more complicated problems. They're not hard, but they take computation. And this is not what you want to do at 10:30 at night when you're worried about getting done by 12. Okay. On some of your tests and retakes, I told you that Abraham is coming. Trying to.
Dr. Brady, did you spotlight the video?
I did. Thank you. Thank you for reminding me. But I did, yes. Now, what was I going to say? Something about the test. It will come back to me. As far as, oh, I know. Some of you made mistakes like doing work, like having 3 or 4 lines of work and the answer is 1/2. And then when you put your answer on the, like if you did a separate page, you did put the answer on the test page and wrote 2 instead of 1/2. And for such situations, for some of you, I wrote, check your work. And what I was trying to do there is say, okay, I'll forgive you this time for such a dumb mistake. And it has nothing to do with you being dumb. It's just a copy mistake. All of us make them. But you can minimize them by going back later when you finish the test and go over it to make sure you didn't make any dumb copy mistakes. Because sometimes people do this on a scrap paper and don't turn it in, and then all I get is 2 instead of 1/2. And I get no other information except that, and then I have to give it 0 credit. Okay, if I saw your work, I'd know, oh, you did send lines of work and everything was 9 lines are correct and you just copied it wrong. So always check your work. That's what you'll see me doing. I make mistakes, but I check them. I go on and, oh, I should have said that. I do it all the time. I did it about 10 times in the last hour. Okay. In the book, we're learning now about maxima and minima and derivatives and second derivatives, which we're going to talk about today. In section 3.1, he talks about those concepts, not the derivatives, but the maxima and minima. In section 2, there's a mean value theorem, which you should learn what it says. There'll be some mean value problems that you'll have to do. But the 2 ideas that we get out of the mean value theorem, because it's a very theoretical one, what we're told with the mean value theorem is if I have a closed interval and a continuous function on the closed interval that also is differentiable on the open interval. So it looks like some kind of nice horizon without trees, no breaks and stuff, just a nice like sand dunes or something, or mountains. Now, the trouble is sometimes mountains have peaks in which you don't have a nice tangent. You just don't have a nice top of the mountain. It might be like a steeple in a church. All right, not something a helicopter could land on. Okay, so On the other hand, if you do have such a thing like this, then the mean value theorem says if I would draw a line between A and B, and I don't care how many times it intersects the graph, that's not the problem. If I draw a line between A and B, there is a slope. That slope would be f of B minus f of A over B minus A. Okay? The mean value theorem says someplace between A and B, so in the open interval, someplace, there is a place where if I differentiate the function at that place, I will get the same number as the difference quotient here. So somewhere now, this particular problem, it looks to me like there might be a place somewhere here. It also looks like there might be someplace in here where I would have parallel tangent lines to the graph, to the secant line between the 2 points. Now, the trouble with the mean value theorem, in a sense, is it tells us there is such a place, but it doesn't tell us how to find it. Therefore, the mean value theorem is used for theory where you don't care what it is, you just care that it is. Okay? If I know, if I'm a young person, I know that if I'm told by some guru that there will be a spouse sometime in my life, a certain degree of uncertainty is gone. Now I just got to find them. Okay? But if you don't know, like if you've just had a bad breakup, you may feel like there is never going to be another person. And so you go through life hoping there is somebody and looking for somebody, but that's two things you're doing. You're hoping and looking. But if you knew that you would have a spouse, like in some countries where a marriage is arranged, you know when you get a certain age, you're going to have a spouse. That's the way it is. Okay? Then that does change your life some. Okay? If you're always going around looking, you know, like if you put on your dating thing on the computer, what requirements do you look for in a spouse, and you say alive? This will allow a certain degree of as long as you find somebody alive, that's all you need. Well, that might be easy to find. But if you say the person needs to be 8'3", that might cut down your expectations. Okay. I've only met one person who is 8'3" in my life. His name was Tiny. Anyway, I can tell you about Tiny sometime, but he's one of the tallest people in the world at the time. So maximum, tallest people in the world, maximum, minimum, this is what we're interested in. The mean value theorem, as I said, doesn't tell you about Tiny, it just tells you there is someplace. Okay? Now, but that turns out to be very valuable. And there's two theorems in section 2 that we use. One comes from the other. So there's one theorem, main theorem, that we use. So I'm going to also write this a little bit differently. This also says that I can write the mean value theorem this way. That if I have that the derivative, the slope is equal to the slope of the secant line, I can multiply by the denominator and get this result right here. And this turns out to be a useful result. So, where is it useful? Suppose we know that we have a function whose derivative is 0 at every point along the line. I'm sorry, every point along a curve. The idea is to know what the curve is by this idea. So if I have a function and this is always 0, always, for all x in AB, right? then what can we say just quickly? If this is 0, any place, then f of b is equal to f of a. And that's true no matter what points I take. If I take a point x1 and take a point x2, x1 is less than x2, I can apply the mean value theorem on these 2 points and get f of some point in between. There might be a d or something between x1 and x2. I don't know if you guys can see this at home. I hope so. Anyway, if the derivative is always 0, then f of x1 would equal f of x2. And so what we get out of this mean value theorem, if the derivative is always 0, not just 0 one place, but always 0, then the function is constant. Okay? The function is constant. That's going to turn out to be very important to us when we do the other half of calculus, which is called integration. Anyway, but it's pretty simple. I mean, I even misspoke when I said it. I said if the derivative is always 0 on the line, on the curve, then the curve is a horizontal line. That's what this theorem tells us. And you can't prove it without it. Okay? So, what else can I do? Suppose I have two functions now. I have a function f and I have a function g. What I know is that the derivative of f and the derivative of g are equal for every place in an interval. Like an open interval. What can I conclude from that? So I have two curves, and at every point on each curve, the slope is the same. In some sense, we're kind of saying the curve's got to be parallel, whatever that would mean. We haven't defined parallel curves, but I think it's sort of like railroad tracks or something, or the left and right side of a highway. Highway may be curved, but you know, everything is just as far apart all the way along the road. The road's a certain width. How will we prove this? We use what we just proved. What you do is you define a third function. Third function is the difference of the f and g. What's the derivative of the third function? It's going to be the differences of the derivatives of the f and g, and that is 0. And so what do I know about h? H prime is always 0. So h is a constant function. H is a constant function. So h of x equals c for all x. So that means f of x is equal to g of x plus c for all x. In other words, if two functions have the same derivative on an interval, then they differ by a constant. Now, in chapter 1, we did not review it very much because we just said you're supposed to know this stuff. What happens to a graph if I add a number to everything on the graph? It goes up. It doesn't change its slope. See, we didn't know about slope then necessarily. It just raises every point. So if the original function is going down and you raise everybody by the same amount, still going down. Okay? And it provides a means of talking about parallel, sort of. Parallel curves, sort of. I say sort of because we have to define it, we have it. In any event, that's the second theorem that's in this page. The two functions with the same derivative everywhere differ at most by a constant. The graph, whatever the graph looks like of one of them, the other one will be the same amount added all the way along. And so when you try to find it, hopefully, mine kind of screwed up here, but when you kind of find it, it's the same. Now, I kind of screwed up unless we think of this as being closer than that. because when you try to picture things on a flat surface of a three-dimensional picture, things that get further away look like they get closer together. So this could be a fence where we go further away. See? And you could have some birds and things. Anyway, that's perspective. Okay, perspective is a problem like on televisions because you are trying to think stuff in 3 dimensions, but it's actually flat. This is why in Hollywood they learned early on that they could stage fights without hitting anybody as long as the 2 people were in the 3rd dimension. If I have 2 people like this and one person swings, that you'll see whether they get hit. If you have 2 people like this behind the camera, person can swing, and if the other person falls over, it looks like you hit them because there's no depth in the 3 dimensions. So they learned about aspect ratios and things like that. And it enabled people, even back in the 1920s, to look like there are fights without anybody getting really hurt. Okay. When they've now digitized everything, they messed it all up. Now you can do anything you want because you just fabricate it. It's a lot more fun when some people actually had to do stunts. Not necessarily fun for the stunt people, because sometimes they would hurt themselves. But I personally do not get too excited. Maybe you guys like these movies where people run along walls and stuff. You know, I want to get by you, so I just go up on the wall and run around. I personally don't find that very, not much fun to watch. Anyway, different situation. Other than that, what we've talked about in this section is pretty much what's in there. You have Rolle's theorem, which is a special case of the intermediate value of the, mean value theorem. You have the mean value theorem, and then we have these 2 things that come afterwards about the derivative always being 0 on an interval and 2 functions having the same derivative on an interval. We will use those last 2 things a lot in the next few weeks. Okay, and then, but other than that, as far as actually computing something, they're not very computational. They're more theoretic in terms of what they give you. Okay? So I want to talk about section 3, which is really a part of section 1. And that has to do with bringing the concept of a derivative into the problem of how does the graph look. Okay? This graph I drew here has derivatives everywhere, supposedly. But just saying that doesn't tell us what the derivative will add to the picture, or if I could create the picture if I knew about the derivatives. Okay? Now, there is a problem, as an example, and it says, suppose I have the following. It will take me a second here to write it. But suppose I have a function, and f of 0 is 0. Okay? And f of 2 is 3. F of 2 is 3. F of 4 is 6. Okay? F of 4 is 6. F prime of 0 and F prime of 4 are both 0. Suppose I know this about a function. Could I graph the function? Or to put it differently, if I ask each of you to draw a picture of what this tells you, would you all, if we collected it later, have the same picture? Is the graph you get unique? Is there enough information here that we'd all get exactly the same result? Or might one of us have a totally different look than another person? That's the question. Okay? So if I'm starting out a graph, okay, so for a while, we're going to be putting things on a graph. You can buy graph paper if you like. In any event, what you ought to do is mark off some things sometimes. But what I'm doing now sometimes is not very smart, because you waste a lot of paper if you draw the picture before you know what the picture is supposed to look like. If I learn that the function is like the square function, so all the points are above the axis, then making a big axis down here would be kind of wasting paper, because I can do the problem without this part. Okay? So what we should do is do a little bit of work to figure things out before you start drawing. But a lot of people just start off. If I just start off, then I'm going to have these 2 points on the graph. This is 2, 3, and that's 0, 0. And f of 4 is 6, so I got to have some more stuff up here. So f of 4 evidently is up there. That's 4, 6. And I know that f prime of 0 is 0, so that slope is 0. That says the tangent line is horizontal there, and the tangent line is horizontal here. That's what I'm told. How specific is that for telling us what the graph looks like? Yes?
I'm a little bit confused because I didn't see anything that said that the slope at 2 was 0.
Sorry, effort. 4. Sorry, thank you. F of slope at 4 is 0. Yeah. We don't know anything about the slope at 2, evidently. Anyway, thank you for correcting me. But the point is, how many different graphs could we draw? Several? Yeah. Okay. We said nothing here about the slopes being positive any place or negative any place. Right? If I knew something about where the slopes were positive and where they were negative, it might help me draw the picture. When the slope is positive, we're going to find out that the graph is going up. Now, I erased it, but the thing I erased, let me rewrite it. F prime of 0 times b minus a is f of b minus f of a. Now, okay. Suppose you know that if I have a derivative, that the derivative is always positive. Then what do I know about this right here? So I'm going to put that over here what this fence was. Suppose I know, and not just at A and B, but suppose I know at any x1 and any x2, all right, that the derivative everywhere is greater than 0 for all x between A and B. Suppose I know that. Then f of x2 minus f of x1 equals f prime of c times x2 minus x1. I'm rewriting the mean value theorem for x2 and x1. Okay? What do I know if this is always positive? This point is between there somewhere. If this is always positive, and x2 is bigger than x1, then the right-hand side is positive times positive, which is positive. What's that say about f2 minus f1? Is positive. What that says is f2 is greater, f of x2 is greater than f of x1. What does that mean? The function's going up. Not just 2 points, but everywhere in between. Now, I don't know how it's going up, but it's going up. Okay? It's not doing this. So again, the mean value theorem tells me if I know something happens in a whole interval, if the derivative is positive in a whole interval, then the graph's going up. Similarly, if the interval is negative in a whole interval, the graph's going down. We use the mean value theorem for that. So derivative positive interval means increasing function. Derivative negative interval means decreasing function. So now, with my picture, as I said, I don't have much information, but suppose I was told the derivative is always positive or 0. Okay? it might be zero, like a zero here, but in between here, if I was told it's always positive, what could you do? You could say, well, I'm going to draw myself a graph that does it. If I knew the derivative is always positive. So if we add to the information something about the derivative, it can help us figure a graph. Now, it wouldn't have to be like this. It might be like this. It might be, you know, all kinds of stuff. I don't know.
It has to be increasing.
Could it be?
It just has to be increasing. Right?
Just has to be increasing. And that can be lots of stuff. Now, again, I've emphasized this happens on a whole interval. If I know the derivative is positive at one point only, just one point, I cannot conclude the function's increasing. Okay? And I won't do that today, but the point is, if I have a graph, and here I have a point, and the slope at that point is positive, 1 point, that's all I know. Don't know what happens next to it on either side. Okay, so I got 1 point, x1 or something, f prime of x1 is positive. Well, I know that. There will be a neighborhood. There will be locally a region where anything to the left will be less and anything to the right will be more. But that does not say increasing, because I could have things like this. In this neighborhood, I could have the thing decreasing. I don't know, but all I know is that it's above. If you know the slope is positive, that means when you leave it, you're going bigger. And before you get there, you're going smaller. But you might be going up and down to get up there. And I can give you examples of functions that do that. Okay? But, so if we say it happens on a whole interval, then the function's increasing. Okay? Now, what if the function's increasing before you get to x1? Over here, the function's increasing. And over here, the function's decreasing.
I think that's one is a maximum in.
And if the derivative exists, it's going to be a high point. Yes? If going in, you're going up, and going out, you're going down, you went through a high point. And that's where, if the derivative exists, it's going to be zero. So the Fermat's theorem says if the derivative is zero, if you have a maximum, local maximum, the derivative has to be zero if it exists. Okay. Now, I can have situations where I'm going up and going down where the derivative doesn't exist, like a cusp. But if the derivative does exist, the derivative has to be zero there, and you have a maximum. So, what we do when we give when we give an equation, a function, in terms of, you know, some expression, f of x equals something, we look first of all for critical points. This is section 1. That's places where the derivative is zero or does not exist. We always evaluate things at endpoints. Okay. We might look to see whether the function has a derivative everywhere or not. If it has a derivative, it's continuous there. So if you know it's differentiable, you know it's continuous. That's a theorem that we talked about. If the first derivative is positive in an interval, the function is going up. If it's negative interval, it's going down. And that's a lot more information than we had a little while ago, if this is the first time you've ever heard it. Now, we want to know more than that, though. And that has to do with what's called the second derivative. Okay? Now, the second derivative being positive in an interval says the first derivative is increasing. If the slope is increasing, what does the curve look like? Well, we always like to think of things going up. If the thing's going up to start with, and the slope is increasing at the same time, you get it's curved up because the sharper, more vertical tangent lines means this number is bigger. Okay? And if you're going down and the second derivative is positive, what does that mean? If I'm going down like this, what's happening to the negative slopes? Like this might be -6, that might be -5, this might be -2. What's happening to the negative slopes? They're growing. They're getting bigger. It's small, it's on an x-axis, bigger, like -10 is a smaller number than -5, right? So this would be, the second derivative is positive, and the first derivative is negative and getting slower, getting smaller numbers, closer to 0. Anyway, when you think this out, when the second derivative is positive, you'll either get something like this or you'll get something like this. When the second derivative is negative, you'll get something like this or something like that. So what do people do when they get an equation to play with? And some of you may have done this, you know, because sometimes it's sort of a religious thing that people do. They make a chart, okay? And in the chart, you put some stuff. And what you're interested in is intervals, because these are the things where things happen. We look for intervals where things happen. Like you might be interested where the function is 0. Or you might be interested where the function is positive. So you might be interested in where is it function positive. So that's part of it. But we also might be interested where the derivative of the function is positive. And we might be interested where the second derivative of the function is positive. Okay. Now I'm putting down more than people put. If you had this in high school, let me ask you, some of you had this, make little tables like this?
Yeah.
Some of you, yes?
Yes.
One person. Anybody at home make tables on derivatives and second derivatives and stuff who had some calculus? I don't know. Well, the book, in some section here, on page 226 and 227, the book in one case talks about numerators, and he builds up various pieces because he's going to, so let's do a problem. We have x to the 2/3 and 6 minus x to the 1/3. If f of x is x to the 2/3 and 6 minus x to the 1/3, what kind of information would we like to know about this function so that I can graph it? Now, remember, first derivative positive means going up, second derivative positive means curved up, and so on. So we're going to use those ideas. Well, when I see this, the first thing I see is a couple of places. I mean, might start writing things down, then I'm going to figure out a table here a little bit. But I would see that the zeros, f of 0 is 0, and f of 6 is 0. So if I'm trying to make a graph, I'm kind of interested where that happens. And so I'm going to have 2 places on the graph already. So I've done my part. Now I'll let you do the rest. Kind of divide to share here. So f of 6 is 0 and so on. So I might be interested in that, but really that's fine. It probably doesn't need to go in a table because I can express it very easily by just saying this. Okay. I'm also interested in critical points. Where is f prime of x equal to 0, and where does it not exist? So I need to take a derivative, and you're going to take derivatives no matter what table we make. table is going to have derivatives in it. So we need to take some derivatives here. So what is f prime of x? They run out of room. If I differentiate x to the 2/3, I get 2/3 x to the minus 1/3 times 6 minus x to the 1/3 plus x to the 2/3 times 1/3 times 6 minus x to the minus 2/3. Now, where does that exist and where does that not exist? Well, denominators can't be 0. And in this case, the derivative has some places where the denominator is 0. Where are those places? They're going to occur at 0 and 6, right? So I'm just going to sort of write down here, f prime of 0, I think, does not exist. Some of you like to say D and E on all the test questions. And f prime of 6, D and E, whenever I don't know what I'm doing, I'll just say that. It's, really what you're doing, by the way, is saying you're denying. You're denying that you're going to figure this out. It's like, you may not think that says deny because something's missing. It has to do with the way that I spell subtle. This is how you spell subtle. And if you say, well, it should have a B, I would say the B is subtle. It explains itself. Anyway, and then we, of course, we get to how you text each other, which is worse than that. Anyway, I have a couple of places where the derivative doesn't exist. At least that's what it would appear, because if I stick 0 in there like you like to do, you get trouble. So I don't know what to do, so I'm going to say it doesn't exist. We can worry about that later. If it's x is not 0, what can you say? Now I may find some reason for things in the table. If x is between 0 and 6, right? In terms of the function, if x is between 0 and 6, this is positive and this would be positive. Yes? Mm-hmm. So in this interval, the function, the whole function, if I have this, in this whole interval, the function is positive. Okay? If I'm bigger than 6, so if I'm 6 all the way to plus infinity, the function is negative. Now I'm actually putting f in here just because I wrote it. Maybe we don't need to have all that, or maybe you want to make up pieces. Maybe here, instead of the whole thing, you just want to talk about x and 6 minus x and make up the pieces. Then what you do is you say, okay, when we're between 0 and 6, this is positive and this is positive, and that's how I would conclude this. So maybe I don't need that row, that column. Understand? The idea of making rows and columns is to help you collect the evidence so that you can then draw it. And the book will include a certain amount. In your high school, you may have done that a certain way, but you can put more columns or less. It depends on how much you wish to store in a nice place on a page so you can recall it later. That's the reason to do this. If you don't, you got stuff all over the place. So that's why people do it. Anyway, between 6 and infinity, x is still positive, but this is negative. That's why I would conclude that, you see? So, fine. What about derivatives? I'm running out of space on my table. Well, here's this thing. What about these things? Okay, if x is bigger than 0, what can I say about this stuff? Well, this is still positive, this is still positive, this is still positive. So, yes.
I'm sorry, I don't totally understand the f prime of x equation because it seems to me like.
Oh, sorry. F prime, okay.
Yeah.
Okay, I'm going to differentiate that, try. That's the power rule, leave that alone. Plus, leave the first one alone and differentiate the power rule. Uh-oh. Anybody else see the problem? Actually, she does understand. She says I'm wrong, but she wants to be nice. So she doesn't understand what I wrote because I'm wrong. Why am I wrong?
Chain rule.
I differentiate 6 minus x, what should I get? Minus. I don't like that because that complicates things. Why does that complicate things? Well, a minute ago, I was going to tell you this graph always goes up because it's positive plus positive, you see? But, if you do the derivative correctly, minus, now I got to worry about the dumb thing. Okay, now I have to do 2 over 3 cube root of x, if you like, and cube root of 6 minus x, maybe you like that better, I don't know, and minus x to the 2/3, and now I'm going to mix my stuff here because I don't know how to write that, and so I have a 3 here, and this would be 6 minus x to the 2/3, and I got to try to figure out when is that positive and when is it negative. What you do is factor some stuff. So now we're going to do some algebra stuff. I got to factor some stuff maybe, or make a common denominator. That would be a good idea. What if I make I want to know what this thing is. Why do I want to know? Because I want to know when is it positive and when is it negative. Why? Because I want to know over here when the graph's going up. Right now I'm only in this area, in this region right here. I want to know when's it going up and when's it going down. So I got to find out when this is positive, when it's negative. Okay, guys. Well, okay. I should have written this as 2, 6 minus x to the 1/3, and 3 x to the 1/3 because I was getting kind of cute and clever and stuff, I thought, and then I ran out of, and some of you do stuff like that too. But now, why do I want to make common denominator? Because I see common denominator is, first of all, it's a 3. But if I would put these things together, 2/3 and 1/3 is 3/3. So the numerator becomes 6 times 6 minus x, all right? Minus x over 3 times x to the 1/3 times 6 minus x to the 2/3. So that looks like 6 minus 2x. So if I didn't make a mistake, and I'm not trying to make mistakes now, that's 4 times 3 minus x over 3x to the 1/3, 6 minus x to the 2/3. So what lesson have we learned? Don't pay attention to me. What other lesson have you learned? Be careful when you take derivatives because it's going to change the whole game of what you're doing. So when you take derivatives, if it's a complicated thing, take it more than once and make sure you got the correct answer. I was going to come up with the wrong picture. I was going to have a picture. I was going to then look at the book and it's going to be different. Then I would be scared because I think you found out I'm a fraud. Okay? So don't do that. Find out that when you differentiate the inside, you know, then do that. Now we got this. Now, hopefully this is right. What does this tell me? It tells me I should be maybe dealing with 0 to 3 and 3 to 6 and 6 to infinity. Why? Because the slope is going to change from positive to negative or negative to positive depending on how big x is. Now, if x is bigger than 3, what do we got? This is positive and this is positive. It's between 3 and 6. Yes. And this one is negative. So at 3 here, what happens? Well, first of all, you want to find critical points. What's a critical point? 3. So I better find f of 3. What's f of 3? It's 3 to the 2/3 times 3 to the 1/3. That's 3. So that's nice. So I'm here, the slope is 0 there. Now I'm getting some information. If x is bigger than 3 and less than 6, what do you know? The numerator is positive and the denominator is positive. So I'm going up over here. Okay? When x is between 0 and 3, this is positive. Am I doing that right or am I wrong again? If x is bigger than 3, this is negative. Shoot, I just can't ever get this right. Check your work. Okay? I did, you see? X is bigger than 3, that's negative. I should have written that arrow down. But if it's less than 3, I write the arrow up. Okay, now that's good because if I wrote, this is down all the way in here, if this is up all the way, how do I get back here? When you get information that doesn't match, go back and look and see what dumb mistake you probably made. You have to do this with wide awake and carefully. Okay, so if I'm right, I'm up and down, so what does this make? Maximum. Okay? Good. What do you think happens at these points? Actually, it's where the slope is infinite. So now, what we ought to do to get a good picture of this is take a second derivative as well. But here's the first derivative, and you'll love to take the second derivative. Now, but I simplify, so here's the first derivative. Take the second derivative of this. That's a quotient rule. You got to be careful. Why am I interested in that once I get it? Because I want to know where things, I want to know, is the graph like this? You know? Or is it like this? What? I don't know. If I know the second derivative is negative, I know it's like that and like this. And the slope doesn't exist here, so it's going to be like infinite like this maybe. But this is a little harder problem. And what you get when you graph it, by the way, is this kind of a picture. You get a cusp here and you get something else here. This is example 7 on page 226. We're out of time. But what I'm hoping I'm doing, I'm going to quit the recording because I've been very stupid today.